Hello, and welcome to the video portion for the second Assemblies lab of ME123. In this lab, we'll be going further into the assembly file type, including more complex mates and some useful new tools. Let's start with the new mates. Here, I've got our arm from the last video, already mostly mated together, but we're going to be using some new tools to add some increased functionality to the model. How about we start with the limit mates? Limit distance and limit angle function pretty much the same as the standard distance and angle mates, but these allow you to apply a range to the limitation instead of a single number. We're going to begin with the limit angle mate. It's pretty much exactly the same as the standard angle mate, except it lives under the advanced mates dropdown. From here we'll pick our two surfaces. Let's select this face here and this face here, and then we can set our starting angle. It defaults to 30 degrees, which works well for this. This shows how the angle is being measured, so we can determine if the directionality of the measurement or if the mate orientation need to be swapped. Once again, we'll check both the flip dimension and flip alignment buttons. And once we have that sorted, we can set our new minimum and maximum values. Let's set it so it has a minimum value of 45 degrees and a maximum value of 135. Cool. Now we can hit our green checkbox, and we see that when we left-click drag on the switch, it gets stopped whenever we try to push it beyond the boundaries. This works as one of the ways that you can manually add limit collisions to your assemblies, and it keeps your parts from clipping into one another. I'm going to leave limit distance as an example for you to experiment with on your own. Alright, on to our next mate, the hinge mate. The hinge mate has several uses, but it's most commonly used to connect together standard hinges. It's effectively three mates packaged together. It lives under the mechanical mates dropdown, right up here, and it starts by first choosing two surfaces that we want to be concentric, so these two cylindrical surfaces here, and then two things to be coincident, this face and this face. Lastly, we have the option of also applying an angle limit mate, and we can select two surfaces, this one and this one, and then apply our minimum and maximum. So let's set it so that it goes between 0 and 180. Hit our checkbox, and we can see that now when we test it, it moves between those two angles, but it doesn't go beyond. Alright, next up, let's take a closer look at what these switches do. They aren't currently attached to anything, so that seems like it's a bit of a waste. Let's connect this first switch here to the rotation of the arm joint. SolidWorks has several mate options that link movement to movement. Here, we want to translate rotational movement in one component into rotational movement in another component. That sounds to me like a gear mate. Now, the gear mate does function properly with two gears, but the things that we're gearing together don't necessarily have to be touching. With the gear mate selected under mechanical mates, we can actually choose disjointed circular edges. I'm going to select this face of our switch here, and then in order to get access to the peg at the bottom of the hinge, we can right-click on the base and select Hide, and then choose this surface here, before finally wrapping up the gear mate by selecting our gear ratio. This defaults to measuring the two diameters, but you can manually swap these about as needed. The gearing ratio is a multiplicative modifier on rotations, and here it shows that for every 20 rotations that our switch makes, the joint will also make 20 rotations. We can even hit this checkbox to reverse the gearing ratio, causing it so that the components will spin in opposite directions. In any case, we can hit our green checkbox, and then right-click on the base model in the mini design tree and select Show to return everything to normal. And now we can see that when we move our switch, the arm rotates. One of the cool things to notice is that the limit angle mate that we applied to our switch earlier still functions. Though now the limit applies to the joint as well, as we can't move the joint into a position that would force the switch to break that rule. SolidWorks remembers which mates apply to each part of the object, and it doesn't allow you to move one component into a position that would force another component to break its own mates. Next up, let's explore the mates for the grippers themselves. I'm going to start with the rotational gripper for now. So, I've got all of the parts and mates in for one finger, but we're missing the other two. Now, we can go through and repeat all of the same work twice more to add in the other two fingers. Or we can explore a new tool in Assemblies, component patterns. Just like with feature patterns, there are linear, circular, and mirror options. Let's start with the circular pattern. Mimicking their feature counterparts, you need to provide a direction. In this case, I'm going to use this cylindrical surface here, and then we need to pick the components that we want to pattern. After we have that set and done, we can go over to our instant spacing. We'll leave that at 360 degrees and bump this up to 3. Hit our check mark to finalize, and we can see that it's duplicated the initial component all the way around the hand. One of the coolest parts about the component pattern is that the symmetries remain even when the fingers move, leading to all three of the fingers moving in tandem. They probably shouldn't be able to clip through each other though, so we're going to need to do something to limit that. For this, I'm going to use the width mate. The width mate lives under advanced mates, and it allows you to specify a width, meaning the outer extensive movement, in this case this flat surface and this flat surface, and a tab, the component that moves between the width. in this case this flat surface and this flat surface. Width has a few options. It defaults to centered, ensuring that the tab remains directly between the two width selections, but we can also choose free, which allows the tab to move between the two width extents, but it does not allow the tab to pass beyond them. This option allows you to simulate a limit distance without having to actually implement a numerical value, making it a lot friendlier with editing. While we're here, it would be really nice if we could get this switch to actually control some portion of our model. We've already used the gear mate, so let's use a different one this time. Rack and pinion. This allows you to translate rotational motion of one component into linear motion of another, and vice versa. In an easy real-world analogy, it's a wheel on a road. As the wheel spins, it moves forward. Okay, let's try it. The rack and pinion mate lives under mechanical mates, and it requires that we choose a rack and we choose a pinion. The rack is the portion that moves linearly, so we need to choose an entity that specifies the direction of that component. I'm going to use this edge right here. The pinion is the component that spins, so we need to choose something that defines an axis. Any cylindrical surface or edge of rotation would function here. I'm going to pick this one. Continuing down, we can either choose the pinion pitch diameter, effectively the size of the spinning wheel, or we can choose the rack travel per revolution, or how far we want the rack to move if we spin the switch a full 360 degrees. Let's leave it as is and see how it works. Okay, so now when we move our fingers, it looks like the switch gets clipped into the model. So two things seem to be going wrong. The first is that our movement ratio seems to need some work, and the second is that the switch's starting position seems off. Let's start with the first problem. To set the ratio correctly, we need to know how far this piece moves between going from fully open to fully closed. For this, I'm going to be using the measurement tool. We'll begin by fully closing the grip, and then we can go up to the Evaluate tab on the ribbon and select Measure. From here, we can select any two things, and SolidWorks will attempt to give you the distance or angle between them. I'm going to measure from this surface here all the way to the back surface. We can see that our distance is about 40 millimeters, and I want our switch to move a quarter of a rotation to close the fingers. Now that we have that, we can go back into our mate via Edit and change the rack travel per revolution to 4 times 40. And that ought to solve our first problem, as we can see that the switch now moves about a quarter of a rotation between fully opened and fully closed. Now for the second problem. Effectively, we want to change the starting condition for our assembly. As we discussed in the last video, moving a component to a specific location in an assembly is a bit of a pain, so we'd like to use a workaround. The generally accepted solution is to use dummy mates. The concept is that you can suppress your advanced and mechanical mates, move the components to their desired position using dummy mates, then you can suppress the dummy mates, unsuppress your advanced and mechanical mates, and everything should be set. We'll begin by suppressing our rack and pinion mate. And after we've got that suppressed, we can adjust our finger position to get access to the surfaces that we want, and then we can go in and add a coincident mate between this surface and this surface. Checkbox. Now we need to move the switch to the position that we want it to be in when the grippers are closed, so I'm going to adjust our switch to have it so that we have an angle mate between the surface and this face here of 45 degrees. Flip our direction and mate alignment as needed to get it into the correct position, and hit our checkbox. Okay. Now that everything's set, our proper starting condition, we can right-click Suppress our coincident and our angle, and then we can right-click Unsuppress the rack and pinion, and we see that now when we move the switch, the claw moves without clipping into anything. And the switch's motion is also mapped up to what we would prefer. One quality of life thing that we can do is to move all of our dummy mates into a single mate folder. This makes it easy to suppress and unsuppress all of them at the same time. To do this, you can hold down the Control key and select the two dummy mates that you want to include. From here, we can right-click and select Add to New Folder, and this time let's label it Dummy. At this point, we can then just suppress our advanced or mechanical mate, unsuppress the dummy folder, resuppress the dummy folder, and unsuppress the advanced mate to go through the same process without needing to pick out each mate on their own. Alright, next up, let's move on to the linear gripper. This one's set up to use a slider to open and close the fingers. For this, what we want to do is translate linear motion to linear motion, using a linear coupler. I've already gone through and set up our width mate and our pattern to keep the fingers from sliding outside of the grooves, so all that we need to worry about on this one is the coupler. We're going to follow the same basic procedure that we used for the rotational gripper, by first creating some dummy mates to move our components into their desired initial conditions. First to set the switch up to be in the fully upright position, and then we'll use another coincident mate to close our fingers from this surface and this surface. Then we'll hit our checkbox to finalize, and that gives us our two dummy mates. And now at this point, we can go about finding the linear coupler. This mate lives under the Advanced Mates dropdown, And for this one, we're going to choose two things that specify directionality. So this straight edge here on our switch would go for the first box, and then this straight edge here would go for our third box. With linear couplers, you have the option to choose reference components, but that isn't something we're going to explore in this video, so they can safely be left blank. Lastly, we can specify our ratio. We can do 1-to-1 so the finger moves the same distance as the switch, or we can swap things around so the finger goes twice as far as the switch does. The exact values that you place here depend on your desired behavior. If we want, we can swap the directionality as needed, and then hit our check mark to continue. From here, we can go about suppressing our dummy mates as we did earlier, and now when we move our switch, we can see that the grippers extend and retract as we desired. Okay, next up, let's look at the path mate. This is one of the more complex mate options, but it allows for some really cool functionality. Effectively, we can have a point on one object follow a specific path, and we get a level of control over that object's orientation as it follows the path. Here, I have a separate path configuration set up with a little wire structure that's been fully defined at a set distance from our arm. What I want to do is have the bubble wand and the gripper follow the wire without actually touching the component. Let's get started. The path mate lives under the advanced mates option, and from here it wants us to choose a component vertex and a path. For the first one, I'm going to use the origin of our follower part, which we can find under the linear gripper follower here. And then for the path, I want to choose this composite curve. Unfortunately, it doesn't seem like our interface is allowing us to actually select the entire composite curve. The path mate allows you to set a single sketch entity, such as a line, arc, or spline, but we can't just directly select the entire curve on its own. Fortunately though, SolidWorks does have a workaround. If we hit the Selection Manager button, we can then choose each line segment individually. So we have our straight edge at the beginning, and then we have our 3 arcs, so 1, 2, 3, and then the straight edge at the ending. Now that we have that, we can hit our green checkbox on the little pop-up window, and we can see that our follower has moved, so now it's centered on the path. Effectively, at this point, we've got a constraint that's holding this point on the path. However, our gripper can still rotate freely. What I want to do is make sure that our wand is always orthogonal to the path, making sure that it doesn't accidentally clip through the sweep. For this, we're going to need to modify some of the advanced options. Path constraint allows you to set specifically where you are along the path, and it can be helpful for animations. Pitch and yaw control is the option that we want to modify, as it defines the 2 axes of rotation that aren't tangent to the path. I'm going to set follow path, and then we can choose which of our direction vectors we want to be tangent. In this case, our little blue arrow looks promising, so we'll hit the Z option there, and that looks pretty good. The last option that we have is roll constraint, and that allows us to control the object's rotation along the tangent path. Not particularly relevant here. Anyway, we'll hit our green checkbox up at the top left, and now we can see that the wand can follow along the path, although the arm does seem to be having a little bit of difficulty. Admittedly, it can get a little bit buggy, but there are a lot of moving parts here. SolidWorks is trying its best to run the inverse kinematics and position everything properly. Actually, while we're here, do you know what's cooler than 1 robotic arm? 2 robotic arms. Let's swap back over to our rotational configuration and see about using that mirror component tool. First off, just like with our feature mirror, we need to choose a mirror plane, which can be any plane or flat surface. Let's pick this one for convenience. Next, we need to choose which parts we want to mirror. I'm going to select all of these components of the arm itself, and the base as well. We probably don't need switches for both of them. Now that we have that, we can hit our right button over here, and see that we've got quite the menu to work with. Let's leave this top section for later, and start directly at the component orientation section. For each component that's being mirrored, we can choose how that mirror functions. Let's look at the base first, since that's the component that's asymmetrical. It defaults to spinning the component around, not quite mirroring it exactly, but it tries its best without designing a completely unique piece. We can also have it flip the component, inverting its orientation about the component's origin. I recommend just experimenting with all of these options to see what they each do. The important one, in my opinion, is create the opposite-handed version, which is going to create an entirely new part file that's a mirrored image of the original. Okay, now back up to the top. These options up here allow you to change what surfaces or axes these pieces are reoriented about, and it's easiest to see with the gripper. If we set the gripper to be mirrored and flipped across both axes, we can see that the bounding box option keeps it in about the same place. Center of mass moves it to closer to where most of the original material was, and origin just does exactly what it says on the tin. It is going to depend on how you position the origin of the original assembly. Anyway, from here we can hit our green checkbox, and when we try to move our components, we can now see that the 2 arms move in tandem. The mirror tool is going to do its best to keep everything symmetrical. Last trick, if you don't want that symmetry enforced, you can dissolve the mirror itself to just be left with the copied components. This is done by right-clicking on the mirror and selecting Dissolve Mirrored Component feature. You can choose to copy over the mates if you would like as part of this process, but in the end you're going to be left with 2 unlinked arms. Alright, that ran through all of the mates that I wanted to use on the arm model. Let's swap to this one. This here is a little ship diorama box. When I spin the handle over here, I want these waves to go up and down, and I want the ship to start moving along the slot. Okay, we'll start with the waves. What we have here is a cam system, where the little followers or the bottoms of these rectangular pieces are supposed to stay in contact with these rounded shapes down here. You could attempt to use a path mate to connect these two together somehow, but SolidWorks does have a cam-specific mate that works great here. It lives under Mates, Mechanical Mates, Cam. The cam path is this weird egg-shaped little bit, and as you can see, you can choose any one of these surfaces, and SolidWorks will select the tangent faces for us. And then the cam follower is this surface here. That's the one that we want to be in contact with the cam face. Alright, now that we have that set up, we can hit our check mark to test it out. Well, that looks like it's running pretty smoothly. And now we can just go about doing the other 7. I'll just save us the time by unsuppressing the others. And now when we see what happens when we test it, we get this nice little wave motion. Alright, next up, let's do the boat motion. First, I want the boat to stay within the slot. It's currently kind of just moving around freely. We could try using a tangent mate along this flat surface and the peg itself, and then use some kind of limit distance or width to hold it in place. But we can also see, when we hit in the Mates menu, that there is a slot option down under Mechanical Mates. The slot option allows you to constrain a peg or a dowel to be within a slot, as hard as that might be to believe. Now, this only works with the standard slot and an arc slot. It does not play well with custom-made slots, just as a warning. Those often require a path mate workaround. But in any case, when we hit our checkbox, we can see now that the boat is constrained to remain within the slot's boundaries. Now that we have the cam and slot mates in place, let's take a closer look at our model. We can see that there's this secondary rod inside that's geared to connect up with the main cam drive. I want it so that as this rod spins, our boat moves down the path. For this, we're going to use the screw mate. Like the rack and pinion mate, the screw mate translates the rotational motion to linear motion. Unlike the rack and pinion mate, however, it uses relative rotation, so how much one component has rotated in relation to another component. Let's apply it and see what happens. Once we've selected it from the Mechanical Mates dropdown, the easiest option is usually to choose 2 cylinders, but anything that specifies rotational motion could be used. Next up, we can choose our ratio, defining either the number of spins that it takes to move 1 unit, or how far you would move under 1 spin. These 2 options are reciprocals to one another, so you can choose whichever one makes the most sense to you. I happen to know that with our gear ratios and spacing, a distance per revolution of 20 millimeters matches the boat up well with the waves. Great! Now we'll hit our green checkbox and test it out to see if it works. As we can see, spinning the handle gets the boat to move along the rod, and it causes the waves to go up and down. As a warning, the cam mate can get a little glitchy on occasion, but oftentimes suppressing the cam mates, repositioning the components, and then unsuppressing them usually fixes it. We can also see that the boat is kind of moving against the waves, so we can go back into our screw mate and uncheck the reverse box to set it up so that now it's going in the correct direction. Though you can see that it did mess up the cam mates in the process. Now that we've got all of the mechanical things worked out, we can go about setting up our initial conditions. First step is to suppress the mechanical mate that's driving the thing, in this case the screw mate, and then we can go about adding our dummy mates. Let's do one concentric between that cylinder and this surface here, and then we'll do another one, this case being a parallel between that surface and this surface, swapped around to ensure that the waves are starting properly. Checkbox. And then we can go in, suppress our 2 new dummy mates, unsuppress the screw mate, quick fix the cams, and now we can see that as we spin the handle, the boat matches up with the waves. There we go. That about completes our assembly. The last thing we need to do is save our files and pack everything up to make it easier to share with others. For that, we're going to get into SolidWorks' Pack and Go feature. This feature copies all of the relevant files and sticks them into a zip folder, rewriting all of their connections to open properly when someone else wants to use your files. To use Pack and Go, we'd first need to go to the Files section, and then select Pack and Go. And from here we can look over the menu. You're always going to want to make sure that we have the Include Drawings box checked, and then also make sure that you have the boxes checked of other things that you used. After that, we go down to the Save to Zip file, browse to choose where you want to put it, and then select a name. Let's just call this one Cam Example. Finally, we hit the Save button, then Save once again at the bottom of the pop-up, and we're good to go. If anyone opens up our newly produced zip file, they'll be able to access all of the parts, assemblies, and drawing files without having to manually relink them. With all of that said, we now have 3 mates left: Symmetric, Profile Center, and Universal Joint. I'm going to leave the practice of those mates up to you. Descriptions of these mates are available in the lab chapter, and the internet is always an excellent resource when it comes to these things. With that, make sure to try these tools out yourself and see what you can do with them. That covers everything that I wanted to talk about for this video. Happy modeling, and we'll see you again next time.